Okay, so now let's begin lecture 18, second in a series of lectures on Monte Carlo method and Monte Carlo simulation. This is the course NE402, Intermediate Nuclear Engineering, on diffusion and transport of radiation and Monte Carlo simulation. In the first few lectures on Monte Carlo, which were number 15, 16, and 17, we went through the basics of random processes, random variables, sampling, central limit theorem, basic probability, distribution functions, cumulative distribution functions. And then we started the Monte Carlo method, the evaluation of integrals, a deterministic problem. And in the last lecture, we looked at the formulation of the integral transport equation. So in this lecture, I'm going to cover these topics which you can see here, simulation in general, just to introduce it, and how do you describe geometry, and how do you decide what your tallies are going to be, and how do you define your tallies. And once you've defined your tallies, then what kind of estimators do you use to estimate these tallies. So then we'll look at the flowchart and data processing. So I hope that in this one lecture, I cover basic concepts of these 4 or 5 topics. Okay, so my name, telephone number, personal email, official email, and personal website. So you're always welcome to send feedback. Okay, so this is what we had ended the previous lecture with, that we looked at the Monte Carlo simulation of integral equations, and I hope you got it, that this is the collision density in Re omega t, with E discretized over here, written as the index G as a superscript. So the contribution in the collision density in phase space Re omega t is made up of 2 factors. One is the indirect factor, and this is the direct factor coming directly from the source. This we derived expressions for the probability of a neutron falling from some higher energy to some lower energy. This is the transport operator, this is the collision operator, and both of these are operators, that's why they're written with a hat. So here's the basic idea behind Monte Carlo simulation, that we're going to take a large sample of neutrons. That's what I've been saying last few, sample. So we're going to take a large means maybe 1 million. We're going to take a large sample of neutrons, representative of the total population. And then we're going to carry out a simulation on this large number of neutrons or photons or anything that whose transport we are trying to simulate. So it's a general method, so let's keep it general for the time being. That's why codes in Monte Carlo like MCNP, when I was a student, it used to be called Monte Carlo neutrons and photons. Before that, it was called MCN, Monte Carlo for neutrons. Now it's called MCN particle, because it's got electrons also in there. You can use it for photons, and hopefully it will be, I don't know, expanded to what other fields. So the Monte Carlo method approach allows modeling complexity of geometry and collision physics. So this is the great advantage over things that we have been discussing so far. So you can model any geometry you like, and you can look at any complicated collision physics, which of course is not possible in diffusion. And in transport, it's only possible through those expansions that you saw in the angular flux. So what I would say is that the Monte Carlo simulation is not limited to idealizations of the sort that limit deterministic approaches. But it's got its own drawbacks. One of its drawbacks is that it requires a very heavy computational effort. The other is that it does not give you the solution everywhere. It gives you where you want it. So this computational effort problem can be addressed, can be eased by the use of powerful hardware and by efficiency improving techniques which result in considerable speed up, such as the importance function I just mentioned. Okay, so let's look at this picture. Okay, now here's a picture of three neutrons, A, B, and C. And this is a medium in which you've got bigger circles. So the bigger circles could be uranium atoms, iron atoms, atoms of anything, but they're bigger than neutrons. So now let's see what can happen. So here's a neutron, and the path of a neutron is shown in red arrows. So this neutron A1 and all its children will be called A something. So this goes to his or her first generation, second generation, third generation, fourth generation, and so on. So it comes here, it strikes over here. Any of a number of things can happen. It could scatter off. So neutron is a black dot. So in the possibility A1, the neutron, so what is happening over here is that three neutrons have come out. So this is the case of fission, which leads to three neutrons. So imagine that it comes and strikes a U235 nucleus or a U235 or a U238 or a Pu239 nucleus, and it undergoes fission. Now in fission, it produces three neutrons. The first neutron goes and collides with another nucleus, and there you see it gets captured. The second neutron, A2, goes, strikes this one, and produces two more, out of which the first one goes here, the second one scatters off, comes here, this goes into recoil and goes over there, and look at what happened to the third neutron here. So you see the picture gets quite entangled. The third one comes here, the neutron goes in the green arrow, and the nucleus goes in the blue arrow direction. So this one little neutron created so many neutrons and trajectories. Now, how on earth am I going to store all of this? Because if there's millions of them, and they go on multiplying, and this time is a very, very small time. Okay, fission takes place over a very small time. So in such a small time, and if I'm simulating over 10 minutes, so imagine how many things I'll have to store in my memory. Maybe it won't be possible. So these are the generations. And so I need to come up with some strategy in simulation where we can handle multiplication of neutrons. So this is called multiplication of neutrons. This is the case of fission. Now, this was purely a random process. As I mentioned to you, why did things happen like this? I don't know, and nobody does. So in a stochastic picture, things happen based on the laws of probability. And what happened to the second neutron? Let's call the second neutron B. Now, supposing they were all simultaneously released, and there's not going to be one or two or three neutrons. Remember, for californium 252, we saw that even a small amount like milligrams would give you 1,000,000 neutrons. So imagine these are 1,000,000 neutrons. They multiply and they multiply and they multiply. So imagine the second one goes over here, undergoes fission, but so it scatters off, scatters off over here. You get one neutron here, undergoes fission, produces one, another here, another here. So this is the picture of simulation, which I could not have told you in words. So this is the path of the neutron, it goes. Now, if you look at if you make a boundary around this over here, so I could say that anything that escapes this boundary, for me, that neutron is dead. Okay, it's finished. I'm not interested in it. And of course, with the assumption that this is a convex boundary. In other words, it is a non-re-entrant boundary. So something which leaves here cannot come back. And it's also called a free surface. Remember I told you what was the boundary condition I told you for a free surface for transport equation? For the transport equation, it was n dot omega hat positive, negative is 0. So n dot omega hat less than 0, uh, n dot omega hat in the negative direction is equal to 0, because n dot is a unit vector pointing outwards. Okay, and what would be the unit vector here? Pointing outwards is in that direction, the left direction. So you could apply transport theory here, you could apply anything that you want over here. Okay, so if you look at a random process, what's actually happening is that this was a random history. Okay, history meaning from the time of its birth to the time of its death. And these are events, like this is what happens to human beings also. We are born over here and we die somewhere over here. And what do we do in between? We go to school, we go to college, we come out with a degree, we get married, we have children, we get old, and we die. So that's the life of a human being. And that's the life of a neutron. And a neutron, once it escapes our domain, we say it's dead. So these are so many histories. So in Monte Carlo simulation, what we do is that we call this a history from birth to death. And we call these events, all the collisions you're seeing here, we call them events. Now, any collision could have taken place. So the question is, why this? And that's why I discussed Wiener processes with you, and we started this by looking at random processes. Now the question is, which I ask you, that do you think our world, our solar system, our life is stochastic, or do you think our life is deterministic? Now, if you don't know the answer to that, then there are millions and millions of people who don't know the answer to that. And this was the debate which I told you took place between people like Einstein and people like Dirac. Einstein had a famous thing which I read in my university days. He said that I do not believe that God plays dice with the universe. So Einstein did not believe that these things are stochastic. But Dirac, Heisenberg, and all the people who came up with uncertainty and quantum physics and were also proven right, they said that nature is stochastic. Just like the famous uh, duality of light that we studied in school, where Newton said that light is tiny stones and particles, and he called it the corpuscular theory of light. And Huygens, who was on the other side of the channel in Holland, he said, no, 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 light is not particles, it's a wave. And that confused us as students, because sometimes we used to say they're particles and sometimes we used to say they're waves. So in school, I couldn't ask that question from my physics teacher because I thought, it wouldn't look good. But now I know that both the theories are okay. And similarly, what we are studying now, deterministic is okay and stochastic is okay. Now, I went in my research in this line, so I'm okay with this. Okay, so this is what we call transport, and this is what we call random processes. Now, if you carry out this simulation, you'll get some result. If you do that again, you won't get the same result probably. And if you do it the third time, you will get neither of the two results. So what is right and what is wrong? So that's why central limit theorem, the law of large numbers, Chebyshev inequality, we need all of those things. Okay, so we are going to simulate using Monte Carlo simulation. Now, where has this been used? Because you might be thinking that, is this just for discussion's sake, or is it actually used? So I'll tell you something, that this is actually used. And when nobody knew what the critical mass of uranium was, and when they were designing a nuclear weapon, so this is why the method was made, because Monte Carlo simulation helped them to be able to estimate the size of the nuclear weapon that they wanted. Now that's how Monte Carlo simulation was used. It's a very, very powerful tool, by the way, and I'm going to show you some applications where you'll see that it is probably the best to design a nuclear system. I'm quite sure of that. Okay, now Nuclear reactors are also designed. Nuclear reactors, nuclear weapons, nuclear systems, for forensics, for thermal neutron activation analysis, for medicine. So it has so many applications, and it's got a lot of precision. So from 1940s to now, which is 80 years, Monte Carlo applications are now so refined and so developed. Now, when I did my PhD uh, over 30 years ago, then, so by that time, 50 years had been invested in Monte Carlo simulation. And in 1984, Monte Carlo perturbation was developed. And I met Dr. Reef at the Joint Research Center in Ispra near Milan. The late Dr. Reef, a very loving person from whom I learned Monte Carlo perturbation theory, on which I did my PhD and which is used for optimization. So in those days, it was a great thing. Now, of course, you might think it's not such a great thing, but it was a step forward. So now we can compete with the Lagrangian. We can compete with optimization methods developed by Euler and Lagrange. So Monte Carlo can compete, and it has the advantage of supercomputing, big computers, generality. So I would say that it's the best thing that I've come across in my entire education and in my research. Now, I don't know how it's used in econometrics and forecasting in biology and medicine, but I know how it's used in engineering and science. So that's where I'm going to take you. Okay, so as I said, one of the great strengths of the Monte Carlo method is to model realistic geometry. So let me show you how it's done. Now here's some geometry which might look pretty complex to you. So there's a room. Inside a room, there's a cylinder. There's a cube. There's a sphere. There's an inverted cone, and there's a right pointed cone. Now, if I tell you that the thing I'm interested in is cell 2, but take out 1, 3, and 4. So do you think you could do it with any deterministic method? I don't think so. But I can do it over here by a very simple few steps, which I'm going to show you. So in Cartesian, in the Cartesian world, and you know, Descartes was a French mathematician who said, let's put everything in X, Y, Z, and called it, and it's now called Cartesian. So in Cartesian, in the X, Y geometry, X, Y, Z geometry, what we do is that we describe surfaces and regions by mnemonics. And we use combinatorial geometry, which is based on Boolean operators of intersections, unions, the complement operator. So through these, we can define anything that you want, including this thing. Okay, so let's see how it's done. Now this I've taken from the MCNP volume 1. Okay, so let me make it a little bit smaller. Okay, so what you see over here are planes, sphere, cylinder, cone. And let's go down and you'll see ellipsoids, hyperboloids, paraboloids, cylindrical cones, then variations of the hyperboloid, ellipsoid, and paraboloid, and elliptical or circular torus, a donut, Dunkin' Donuts. So you'll see these kind of things. Okay, now how do we write down their equations? So here's what everybody knows, a straight line. So a straight line is x plus y minus 4 equal to 0, right? If you say it's x plus y equal to 4. Now a plane, let's use the mnemonic P for a plane. A plane you would write as ax plus by plus cz minus d. We're going to bring everything on the left-hand side and put it equal to 0. Why? Because anything, any values a, b, c, d, which satisfy the left-hand side and make it equal to 0 are values that lie on the surface. Now for any values a, b, c, d, where instead of equals you say less than 0, then that point lies beneath or to the left or to the less of the plane. And I'm going to define all these terms. What do I mean to the left, to the less? Imagine a circle. Okay, we'll come to that. Okay, and if any combination of these values gives you greater than 0, then it's outside. Okay, it's above the plane. So how do I describe something relative to a general plane? Well, I can input the coefficients a, b, c, d of this equation. I can put in the values of a, b, c, d, and the three possibilities that's going to happen when I put them at a point x, y, z to determine if the point x, y, z is to the left of it, on it, or to the right of it. Now, when I put the point x, y, z in this, when I put the a, b, c, d, if I get less than 0, so I have a negative sense with respect to this plane. If I get a 0, then I'm on the surface. I'm standing on it. And if I get a positive value, then I'm above it. I'm to the right side. Well, I must use these words left and right carefully because that depends on which quadrant you are. Okay, now the special cases of a general plane could be that the plane is normal to the x-axis, it's normal to the y-axis, it's normal to the z-axis. Now look around you, you see your classroom or a room where you're sitting in, it's got 6 walls. So there's the floor, there's the roof, there's the wall on your left, the wall on your right, the wall in front of you, and the wall behind you. So the first thing you should do is write down the equations of these walls, and you are inside the wall. So now see what is your sense with respect to these surfaces. So if your wall is 10 feet away, so I'll call it x minus 10 equal to 0. So if your position is 6 feet, that means 6 minus 10 is negative, so you're inside the domain on which this is a bounding surface. So this is so much for a plane. Here x is a constant, here y is a constant, here z is a constant. Now for a sphere is a 3D version, 3D extension of a circle. A circle is x squared plus y squared minus r squared is 0. So a sphere is x squared plus y squared plus z squared minus r squared equal to 0. Now, what do I have to define for a sphere that is centered at the origin? I just need to say what its radius is. But for a general sphere, whose radius is at some x bar, y bar, and z bar, so I have to give the x bar, y bar, z bar, and the radius out. So I have to specify, I have 4 entries I have to make. And these are the mnemonics. So a sphere centered at the origin, let's call it SO. A sphere, general sphere, let's call it S. A sphere centered on the x-axis, let's call it SX, SY, SZ. Now the same for a cylinder. Again, cylinder can have its center. A cylinder is a circle which is just extruded. So here's a cylinder. For parallel to x-axis, you give these 3, parallel to y-axis, these 3, parallel to z-axis, these 3. And this is the case when the cylinder is on the x-axis, on the y-axis. So you see now, through these mnemonics, we get to define first, second, third, and fourth degree surfaces. Here's a cone. Now, these are the cones that I showed you. These cones, one is pointing right, one is pointing down. So let's see how do we describe them. So here are cones. Now, the right left is through the plus or minus sign, plus 1 or minus 1. And here is the equation of a cone. It's a straight line, as you can see, but this is the only difference over here. Oh, I must mention something called a direction cosine. A direction cosine when I showed you the 3D picture of a point with the unit vector, then I showed you the omega x, omega y, and omega z components of the solid angle. So direction cosines are on the omega x, omega y, and omega z. And that's what you need for a plane over here. You can also write the equation of a plane. As you know, when you studied vector calculus, you can say it's x minus x naught divided by L. is equal to y minus y naught divided by m is equal to z minus z naught divided by n. So in that case, L, m, and n are the three direction cosines. So that's the equation of a plane. Okay, so I've done plane with you, sphere, cylinder, and cone. Now let's come to some higher level surfaces, like the ellipsoid. What does it look like? An ellipsoid, it's like a soccer ball. Hyperboloid, paraboloid. You know what a paraboloid is? It goes up like a parabola and you rotate it around the z-axis or any axis. So depending on that. So look at its equation. So x squared, y squared, z squared. And there's also these other terms which were not there for a sphere. So this is how it differs. So so you've got to give so many entries for an ellipsoid, hyperboloid, or a paraboloid. Cylinder, cone, whose axes are not on the x, y, or z axis. So again, you can give the equations. An elliptical or a circular torus. Now, this is good for modeling a tokamak. Now, as I told you, a tokamak is a donut. The ITER experiment, International Thermonuclear Experimental Reactor, if you were solving a problem over there, you would use these surfaces to define the central cell. You know, the huge central cell where they put the DT, where the magnetic field is, and where they want the ions to collide so that fusion can take place. They want the deuterium and tritium ions to gyrate about the magnetic field lines, the B azimuthal or the B toroidal or the B poloidal. So they want the confinement to take place through a very strong magnetic field of, let's say, 12 Teslas. And so if you're modeling a tokamak or a stellarator or something like that, then these are the surfaces that you can use. So you can model everything and you can easily model. So now back to this picture. So what you can see is that the numbers in circles that I've written are what are called cells. And I have not numbered the surfaces. So surfaces and cells. A cell has volume, a surface has area. So a surface is inside a cell. Okay? And you enter or leave a cell through a surface. Just like when you enter a room has a volume. How do you enter a room? You cross the door. You cross something, you cross a wall through an opening, through a door. So you cross a surface to enter a room. So the same thing over here, you have to number your surfaces, and for the neutron to enter any region which is circled over here, it has to cross a surface. Okay, so we've got cells and surfaces. So how do you use a Boolean operator? Now anything, if there's a cell 1, a circle for example. So I define this circle by surface number 1, and the cell 1 is inside the circle, right? So I'll say it has a negative sense with respect to surface number 1. Now let's say outside the circle, let's see, maybe I have a picture over here. Okay, so yeah, look at this picture. Now this is a picture of two spheres. They're concentric, so they have the same center. So look at this picture. Now this is surface 1, I've labeled it as 1. This is surface 2, I've labeled it as 2. This is cell 1, the volume inside the first sphere, and this is cell 2, which is between the two concentric spheres. This is a point P inside the first sphere, and I drew the x, y, and z axes over here to show you that a neutron which is traveling in that unit direction is going to cross this, and then leave here. So if this is surface 1, this is surface 2, so this cell has a negative sense with respect to this surface. But this cell 2 has a negative sense with respect to surface 2, but it has a positive sense with respect to surface 1. So I would define cell 1 as something less than 1, and I would define cell 2 as something greater than 1 and less than 2. Okay, so that's how I define this surface. That's how I define this cell and this cell, which is colored purple. Now comes the question that have I defined everything? Because my neutron has to go somewhere. So I have not defined the outside world. So the outside world is greater than surface 2. So if you look at the Boolean description of the problem that I just showed you, of the configuration that I just showed you, so cell number 1 is expressed as -1. Cell number 2 is expressed as +1, -2. In other words, outside surface 1 and inside surface 2. Cell 3 is defined as outside surface 2. And these are the equations of the two spheres. One has a radius r1, the other has a radius r2. Now, when I simulate the neutron or the photon or anything, the electron, I carry out what is called ray tracing. The ray is a straight line that it moves in. Now, an electron doesn't have to move, a charged particle doesn't have to move in a straight line, but neutrons and X-rays and gamma rays have to move in straight lines. So let me say that I'm doing ray tracing, and this is the picture of a ray which I'm showing you over here. It's a line with an arrow meaning that it's a vector, it's moving. So the equation of a plane is this. The normal vector is ABC from the point ABC, okay, over here. So here's a vector. I don't know what I'm trying to see. I'm trying to see that is this going to intersect with any plane. The equation of a plane is ax plus by plus cz. This should be a minus d equals to 0. Okay, so okay, so here's the equation of the plane. Now the normal vector is ABC components in x, y, z. To find d, the distance from the origin of the ray to the plane where it intersects the plane, we first need to find the points of intersection. Now along the ray, x changes by what its initial position was plus it's moved in the direction omega, and if its speed is 1, then it's moved a distance vt, which is written just as t. So this is now the new x, the new y, the new z. So the point that lies on the plane, let's call it xd, yd, zd, lies on the plane, therefore it must satisfy the equation of the plane. Thus, a scalar parameter small t, now this is always done in surfaces, a scalar parameter t can be found where the point on the plane and the direction of the plane is equal to minus n dotted with r naught plus d. D is the number in the equation, and n dot omega. So you can find a parameter t like this, and if t is less than 0, that means there's no intersection with the plane. So it's as simple as that. So what I did with you was this, that you calculate is n dot r naught equal to 0. If it is, then yes, then the ray and plane are parallel and there's going to be no intersection. If it is not equal to 0, then you compute the scalar parameter t. If again the scalar parameter t is less than 0, no intersection. If there is, then you found an intersection. So that's how you carry out one possible event of a neutron or a photon in its transport. Now here's a little example using that for you, that here is a ray. So this thick line vector is a ray. It's at the point 213 at some time 0. It moves in this direction, omega x, I hat, I, j, and k are the unit vectors along the x, y, and z axes. So it moves it moves along this unit vector. The orthogonal angle and the azimuthal angle are both given, so you can calculate the sines and cosines and go back to the components, which you should, by now you know that what is omega x, omega y, and omega z. So you can determine whether it's a point of, whether there is a point of intersection with a plane which is normal to the y-axis. So it's the equation of the plane is y is equal to 2, but written as y minus 2 is equal to 0. Okay, do this yourself. Now let's come to tallies and estimators. What are we trying to find out? Why are we doing this simulation? How can we obtain our tally? So there are three questions I asked you. Why are we doing this simulation? What are we trying to tally? How can we tally what we want to tally? Okay, the first question, why are we doing this simulation? We are doing this simulation because we want to understand the behavior of neutrons and photons in a region of interest. We want to know how much energy they deposited where, and then what the flux was, and then what the reactions were. So that's why we're trying to carry out a neutronic photonic analysis of a nuclear system. That's why we're doing this. The second, what do we want to compute? We want to compute the scalar flux phi. Okay, that's what we want to compute. The scalar flux phi, where? In a region of interest, in a volume of interest. And what is phi? Phi is the number of neutrons per cubic centimeter in some room, in some volume element, multiplied by the speed, v. So what are the units of phi? Neutrons per cubic centimeter multiplied by centimeter per second, which makes them in neutrons per centimeter square per second. So the first question answered, why are we doing this? The second question answered, what are we trying to achieve? We are trying to find the flux. Now the third question is, how do I find the flux? So far you know that the tally of interest, the score of interest is the flux phi. The question is, how can I estimate the tally of interest? For that, I need an estimator. What am I going to estimate? Okay, so for that, I need to understand what I'm trying to tally. So what am I trying to tally? The flux. So a neutron comes, travels a distance. Imagine no fission can take place because it's easy to look at this picture. Imagine a neutron comes here, travels the distance d1, hits a nucleus, strikes back. See, I'm not interested in the recoil, so I'm not even going to mention that to you. And I'm not considering the possibility of a fission. So it comes here, travels a distance d1, hits this heavy nucleus, comes back, travels a distance d2, hits this, hits this, hits this, and then goes somewhere which I'm not interested. So what is happening to this neutron? So if now what I've showed you are tracks. This is the track, this is another track, this is another track, this is another track. So I've showed you 4 tracks of neutrons, and each of them have a length. So TL stands for track length, and E stands for estimator. So a track length estimator is what I need. And because the definition of flux is NV, so N, small n, is the number of neutrons, okay, the number of neutrons per volume V. So there's nothing I can do about it. The number of volumes is from the source, so it's not a variable and I can do nothing about the volume. So let's not talk about N over V. Nothing interesting happening over there. Okay, now what's interesting is the V. The V is the speed, which means the distance traveled per time is the speed. So, and the distances are all different. So the first time the distance was d1, the second time d2, the third time d3, d4. Now, as I've shown you here, it's just one neutron. But actually, let's say 1 million neutrons are coming here, 300,000 get absorbed here, so 700,000 come here, 100,000 get absorbed here, so 600,000 travel this path, 200,000 get absorbed, so 400,000. See, the numbers keep changing. So why should I use such big numbers? Why don't I say that I assign a weight to those million neutrons? Okay, so let me assign a weight to those million neutrons, because then I don't have to talk in terms of such huge numbers to you each time, million, 600,000, etc., etc. So let's assign a weight, and you'll see that this has other advantages also, such as better computational and statistical efficiency. So now, what's the definition of the track length estimator flux? It's the weight multiplied by the distance divided by the volume. Volume is fixed Weight will change after every collision because of absorptions. So million neutrons, if the absorption is 0.3, so 300,000 will go away. So you want to kill those at this absorption? No, that's bad statistics. You want to let them continue with a reduced weight. So that is why the definition of phi as a track length estimator is the weight multiplied by the distance traveled divided by these other things. Okay. So the total starting weight, if I start 10 neutrons, I give each one a weight 1, so I'll say the total weight is 10. The volume of the room is here, so these are constant, I can leave them out. So actually, the track length estimator of the flux is the summation over all these 4 tracks of the quantity Wi times di. Okay, so that's how I'm going to estimate the flux. Now there's another estimator, there's so many estimators. There's another estimator called the collision estimator, that how many collisions took place. So in how many collisions, so how much distance did it travel? So 1 over sigma, capital sigma T is the distance it traveled, and how much weight traveled that distance. So that is an estimate of the collisions that took place. So I can get a collision estimator of flux. I can get a track length estimator of flux. So many codes do a track length estimator as well as a collision estimator. Okay, the other thing that we are interested in is how many are crossing a boundary. How many neutrons, how many photons, because if I'm standing outside a nuclear reactor, I'm outside the boundary, but I would like to see how many neutrons are going to hit my chest, how many photons are going to hit my chest. So I'm actually interested in how many are coming out and hitting people who are standing over there. Now that's called the surface flux. So the surface flux Js again has an estimator, which is how much weight is crossing the surface. So it's as simple as that. So that's how we compute the flux and the current. So I'm going to stop over here because I would like to take some time over here in the next lecture to explain it to you nicely. So far we've just looked at simulation. What is simulation? We've seen how we can model geometry. We've done the Boolean, little bit of Boolean combinatorial geometry, and the unions and intersections of of 2 concentric spheres. So I'll carry this on from lecture number 19 next. Okay, so this is the end of this lecture.